Uh, okay, so first thing we do is we can state all the information we have and all our data and conversions. We have a compressor system that takes atmospheric air at 5 degrees Celsius and supplies it to a distribution system. The entire system is at steady state, and all pipework is cylindrical and made of HDPE. There's 50 meters of 300 mil diameter at the inlet pipe, and 200 meters of 150 mil diameter outlet pipe. No change in elevation of the system. What does that mean? No change of elevation means that there is no change in pressure, and because this is air, we care about pressure because pressure will affect the density, and density can be changed in air because air is a gas, and gases are compressible fluids. The molecular weight of air is 29 kilograms per kilogram mole, and its viscosity can be taken to be 1.8 times 10 to the negative 5 pascal seconds throughout the system. All pressures in the diagram are gauge pressures, so we'll have to convert that to um, outside pressure or absolute pressure. But absolute pressure, that just means like the gauge pressures, like the pressure in the context of the pipe. So here, like relative to all the other measured pressures in the system, is 0, and this is 0.5. Hopefully you guys understand that I still don't really have my head wrapped around gauge pressures, but we don't work with gauge pressures unless we absolutely have to. So what we need is the mass flow rate, density of the air, the volume flow rate, and the average velocity. And what I'm thinking is we have a bit more information here at the outlet, and we can use the conservation of mass to equate the two parts of the system to each other, and then solve algebraically for all the parameters we need. So mass flow rate, density, volume, and average velocity at the inlet end of the system. So without further ado, we'll get into it. So first of all, the fluid is air, which is gas, therefore not incompressible, compressible, which means that the density can change. It is a steady state system, which means parameters are constant with respect to time. WRT just means with respect to. It's just like my sort of shorthand way of writing it. In other words, the parameters do not change with time, so everything is constant. There is no gradient. There is no other graph. If you are thinking about this in calculus terms, it's all 0. It's already a straight line. We've said it's a compressible fluid, it's steady state, and the main principle we're going to use here is the conservation of mass. So dm over dt, I'm using big M to denote mass, is equal to, and I'm denoting little m with a dot on top to denote mass flow rate, which is equal to 0. Let 1 denote inlet, 2 denote outlet, just to keep life simple. And it's important that we lay everything out, because if we give this to someone else, they need to be able to read it, you know, in the workplace, or if you just want a peer review, because I fucking hate going through other people's messy calcs, and it's a bit hypocritical because my calculations are messy. So this is also just a way for me to get into a habit of writing really neat, because I lose marks in exams because I'm a messy writer. Yeah. And just on a side note, the steady state system kind of throws people off, but the conservation of mass still applies in a transient and a steady state system as long as they have closed boundaries. So in this case, this is a pipe system and the boundaries are closed. It's not an ocean. Now we can do our data and conversions. So at 1, we have T1 is equal to 5 degrees Celsius, which is equal to 278. I'm not going to write 0.15, I'm just going to keep it a little bit simple. Kelvin. We have our gauge pressure, which is equal to 0, which is just 101,325 pascals. We know that because 1 atmosphere pressure is 101,325 pascals, and a compressor system takes atmospheric air at 5 degrees Celsius. So we know we are working at our level. We're not on a mountain or under the water. Excuse me, sorry. Or pipework is cylindrical, we can use that to work out area. We don't really care that it's made of HDPE at this point in time. Okay, we'll go L1 is equal to, what was it, 50 meters? 50. And the diameter is equal to 300 mils, which is 0.3 meters. T2, as stated here, is 36 degrees Celsius. which is 309 kelvins. The gauge pressure is equal to 0.5 relative to this 0, so that means it is 1.5 times atmospheric pressure. So 1.5 times 101,000. I'm so sorry. And we do have the average velocity at the outlet, which is 45 meters a second. We'll actually move that down. We'll move that to the side for now because the length is 200 meters, if I recall. Yeah, 200 meters. And the diameter is 150 mil. 0.15, and we have that average outlet velocity. So, we also have, I can write here, data and conversions. We have mu, which is our absolute velocity, viscosity, which is 1.8 times 10 to the minus 5 Pascal seconds. Material, HDPE, high density polyethylene, and the molecular weight is equal to 29 kilograms per kilogram mole. Now, straight off the bat, we're going to use the ideal gas law to find the density of the air at the outlet. With that, we will say R is equal to 8314 kilograms per kilogram mole. If it was grams per mole, I think that's the usual unit. It is 8.314, but that is the ideal gas constant. So, first of all, we'll find the mass flow rate at the outlet. But to do that, we need the density of the air. We can work out the density of the air at both ends. So, let's find it at one first. So, using the ideal gas law, which is PV is equal to nRT, which is equal to mR-T, if we write it in terms of mass. I'm sorry, it's a bit dusty in my room, where R dash is just equal to the ideal gas constant over the molecular weight, which is the same as pressure over density multiplied by temperature. We can fuck that off. We don't need that. And we can just rearrange these two terms here. So we can write density is equal to molecular weight times by pressure over the ideal gas constant multiplied by temperature. So P1 is equal to 29 times 101,325 over 8314 times 278, which should be like 1.27 or something like that. So 29 times 101,325 over 8314. I'm just using my calculator here. 278. 1.27 kilograms per meters cubed. We are writing everything in SI units because it just makes life easier when we convert into the units of context later on, which we're not going to do here, but you know, in other problems. Now, density at 2. Same sort of thing, so rho 2. I'm not writing out that whole equation again, I've already established that here. So rho 2 is equal to molecular weight times pressure. Oh, that's pressure 1, pressure 2. That's T1, T2. 29 times, what is like 151,000? Yeah, 151,988 over 8314 times 309. Yep. So I need to write my rows better. Rho 2 is equal to 29 times 151,988 over. I'm just going to round everything to 3 sig figs, by the way. 1.72 kilograms per cubic meter. Oh, let me just make this a bit neat. It's important to be neat, guys. Okay. Now we can find the mass flow rate at 2 at the outlet. So M2 is essentially equal to density times by density at the outlet times by the volume flow rate. But we need the volume flow rate. So before we work that out, volume flow rate at 2. So Q2 is equal to U2 A2. Now A2 is just equal to pi on 4 d squared on, pi on 4 d2 squared. A2 is equal to, let's move that to the side, pi on 4 times 0.15 squared. So A2 is shift pi on 4 times 0.15 squared, 0.01. Seven. I'm just thinking, why am I doing that one? I could just write it, like, convert it in there. Oh well, too late now. Q2 is equal to, was it 45? I think it was 45 times 0.0177. I've been yapping for too much. I don't normally talk when I do my equations, so this is weird. That looks about right. I've done this question before. I'm just hitting it raw again, like today, so I kind of vaguely remember the values. So the volume flow rate at 2, beautiful. I think that is it. Mass flow rate, volume flow rate. Okay, cool. Now we can find the mass flow rate at 1. First, we'll have to finish this off. So the mass flow rate at 2, so M2 is equal to 1.72 times by 0.797, which is 1.37 kilograms per second. Now we can do the mass flow rate at 1, sorry. Now, using the conservation of mass, to reiterate, it does not matter if the system is transient or steady state, it's just got to be in a closed boundary. Or a closed system, sorry. And it mathematically is expressed as dm on dt, which is equal to mass flow rate at the inlet, take the mass flow rate at the outlet. You can kind of think of it as path independent because it's only really concerning the start and the end of a system, or a path travelled. I don't know if that's the correct way to put it, but that's how I think of it. Which is equal to 0. Now, that means M1 is equal to M2, which also means rho 1 Q1. Wait, that can be worried about later. Therefore, M1 is the same as the mass flow rate at 2, which is 1.37 kilograms a second. Beautiful. Now, we can find the volume flow rate. Basically using the same principle, the conservation of mass. We say mass flow rate at the inlet is the same as the mass flow rate at the outlet. Rewrite that in terms of pressure, density, and volume flow rate. So rho 1 Q1 is equal to rho 2 Q2. And we are concerned with the volume flow rate. So we'll rewrite that as Q1 is equal to rho 2 Q2 over rho 1. We have all those parameters, so Q1 is equal to 1.72 over 1.27. Wait, is that correct? 1.72 multiplied by, is that 0.797? Oh, fuck. Over, what's rho 1 again? 1.27. Yep. From memory, it should be... Actually, I'm not going to say because I might not get it right and I'll embarrass myself in front of my 0 viewers. No, that looks correct. 1.08 or 1.079 meters cubed per kilogram. No, per second. Alright, and now that we have worked out all the other parameters at the inlet and the outlet, all we need to do is work out the average velocity flowing into the system at the inlet. So, simply put, the volume flow rate is equal to the average velocity multiplied by the area. So in this case, the area is pi on 4 d squared You can write it as pi r squared, where you divide the diameter by 2, but we've already been given the diameter, and it's just good practice to write in terms of diameter if you've been given the diameter, especially in practice. You're more than likely going to get materials or equipment or goods where the diameter is stated instead of the radius. In my opinion, it doesn't really matter. It's the same step either way. You have to do a calculation to, convert the radius or the diameter. But without further ado, let's finish this off. So rearrange algebraically. This is very simple. Q1 over just Q1. Whoa, what's my pen doing? So 4Q1 over pi d1 squared, so U1 is equal to 4 times 1.08 over pi times 0.3 squared. So U1 should be a number of some sort. Let's calculate it on the calculator, because I'm not working that out in my head. .29 meters per second. And that should be it. Thanks, guys.